It's my pleasure to be here today. Hello, everyone. Welcome to my talk today on the intersection of FHE and AI. Firstly, I would like to thank the INCO team for doing a spectacular job of organizing this event. So I'm really grateful to be here speaking to you today about the intersection of FHE and AI. And my name is Advait, and you can call me Leo. I'm a computer scientist by training, and I'm the co-founder and CEO of Supersight. At Supersight, we have 175,000 users who currently use Supersight to get actionable insights. And my background is in AI. I previously published 57 works in big data, data science, machine learning, and AI. And I got really into crypto in 2021 through research. And specifically what I was looking at was I was researching graph detection patterns for detecting wash trading in the NFT markets. And this is how I actually fell in love with the intersection of AI and crypto. And aside from like my academic work, I've also been involved in the crypto space as a research partner at Fabric Ventures, lecturer of portfolio management at UCL, and delegate at MakerDAO. And so today we're here to talk about like the holy grail, which is essentially we want to be both person A and person B at the same time. So person A, what they want is they want highly personalized recommendation algorithms for their Amazon, for their Netflix, and they want all of this to be exactly accurate to their liking. And then person B doesn't actually want Amazon to see their searches across different platforms. And essentially, we're often both person A and person B at the same time. And so before FHE, it was actually impossible to be able to build like highly personalized recommendation algorithms without uploading our data to a cloud, where a machine learning algorithm actually learns from our consumption behavior and choices. And so as we know, AI is actually eating the world as it is today. And AI is actually central to a lot of different tasks, such as computer vision, natural language processing, and recommendation systems. However, training these models is actually very challenging for the average user. And this is because, essentially, like you require a lot of training data to be able to train an AI model. So firstly, like the problem that you face is data volume. Secondly, like the problem that you face is that you actually require a lot of computational power to be able to train AI models. And third, essentially, you require a lot of domain expertise to be able to like train AI models end to end. And so essentially, like we came up with this solution, or the industry has come up with this solution of AI as a service. And essentially, this actually removes all of the hurdles. So what we can do is we can inference from models that have been built by larger organizations such as those in the FANG. And essentially, like what happens is like our data or our input data for the recommendation systems that actually give us recommendations based on our personalized choices. So what happens to our data is it's encrypted, but only during transport. And essentially what happens is it gets decrypted on the server side. So on the left-hand side, we have the user side. On the right-hand side, we have the server side. So our data actually gets encrypted during the transport, but decrypted here on the server side. And essentially, they have both the input to the AI model as well as the output. And this is a problem because essentially what that means is they have access to all of this personal data to be able to train AI models, but essentially it's not the most privacy-preserving manner. So I mean, the way that it's working at the moment is like, it's not exactly like data privacy protocols that we observe when we interact with these AI as a service platforms. So what happens is the raw image goes onto the cloud, and then essentially like a predicted label is generated using the neural network, and then the users receive a label, and then they use it in the application. And the problem is that like no one actually wants to share sensitive data. So no one wants to share healthcare data, financial data. These are kinds of data that are very personal to different people. And ideally, like if you are getting like recommendation algorithms working on this kind of data, then what you would want is you would want the computations on your data to be happening in an encrypted fashion. And this is where fully homomorphic encryption actually comes in. So it solves this problem exactly. So essentially what happens is like FHE is a scheme that allows computations on ciphertext. So the kinds of computations it allows is addition, multiplication, and then table lookups. And so what you can do is instead of like sending the exact variables all the way to the server, what you could do is you could send an encrypted version of A and similarly an encrypted version of B, and then the addition would be performed homomorphically on the server. And so essentially, like if you look at this scheme, it's a much more privacy-preserving manner because what's happening is you're adding A and B and getting the output together. And then this comes back in an encrypted fashion. Then you decrypt it at the client level, and then you essentially get the results that you're looking for. And so essentially, like this ensures that data privacy is like handled carefully while allowing computations to be performed on the cloud. And so beyond basic like operations like addition and multiplication, there have been like a lot of improvements and advancements in utilizing fully homomorphic encryption for neural networks within AI as a service pipelines. So in this context, users can actually encrypt their raw input data into ciphertext and then transmit only the encrypted data to the cloud server. And the server then performs computations homomorphically on these ciphertext, generating an encrypted output, which it returns to the user. And so, I mean, this establishes an end-to-end FHE encrypted data flow, safeguarding user data privacy throughout the process. And essentially, like the goal here for us is to be able to build like FHE-based neural networks and AI as a service platforms. And essentially, what we want is like we want the ciphertext to be sent to the server, and then even if the user goes offline, as there's no frequent communication required between the client side and the server side, and then this case would still work. And so essentially, like this is a scheme that enables a lot more opportunities in AI. And so essentially, like in this slide, what we're looking at is an algorithm that describes like how do you build a full protocol for privacy-enhanced neural networks. So essentially, like what you can do first is you have to define the parameters for the input layer, including security settings that ensure our data remains protected. Then these parameters are actually crucial for maintaining the integrity and security of our encrypted computations. The next what we have is we set the parameters for the hidden and output layers, and then these actually include more advanced encryption settings tailored to handle the complex operations that are required in our neural network. And then the next step is essentially we also specify some decomposition bases, which help in managing and optimizing our encryption processes. And then what we do is we start with an input vector, which is essentially a list of data points, and which we encrypt into a set of ciphertexts. So imagine encrypting each piece of data in a way that allows us to still perform operations on it without ever decrypting it. And to facilitate these encrypted operations, what we generate is a set of evaluation keys. And these keys allow us to perform mathematical operations on our encrypted data, ensuring that we can process the data while keeping it secure. Now, the next step is actually creating switching keys. So we can also create switching keys that help manage the state transition between different layers of the encryption. And this enables smooth and secure processing of our data throughout the network. And then in step 7, what we're doing is we're initializing our neural network with an input layer and an output layer defining the structure of our network. We then iterate through each layer of the neural network, and for each layer, we determine the number of neurons and define the weight matrices and bias vectors. And the way that you can think about neurons here is as the processing units of the network, and weights as the importance of each connection, and biases as thresholds for activation. So what we're doing here is essentially within one layer, or within each layer, we process each neuron one by one. We take the encrypted data from the previous layer and perform operations to calculate the inputs for the next neuron. And this involves homomorphically evaluating linear functions. which means we are performing operations on encrypted data without ever decrypting it. And for each neuron, we use a lookup table to evaluate and transform the encrypted data. We then perform key switching and rescaling to adjust the encryption parameters, ensuring that our data remains secure and correctly formatted for the next steps. And once all of these layers have been processed, we return the final set of the encrypted data to the user. And this user can then decrypt this data using their secret key to reveal the prediction results. And this ensures that throughout the entire process, the data remains encrypted and secure, providing robust privacy protection. So FHE for AI actually enables a wide array of new use cases. And so the first use case that it enables is consumer privacy in advertising. And essentially, we've seen in research like models of recommendation engines that have been built that deliver encrypted recommendations to users without the system actually knowing the content or the input data. Then other applications are medical applications. So for example, Nairig et al. Actually propose a scenario where a patient's medical data is continuously uploaded to the service provider in encrypted form. Then also in data mining. So essentially, you can use data mining to learn a lot of like useful facts from like the data structure. But the problem with data mining is that it often like compromises on the privacy for each of those individuals whose data is contained. And so there have been works that actually address this issue by applying functional encryption to find a solution. And similarly for financial privacy, so just as Inco's use case actually enables, so you want to keep like some parts of your financial information private, and Inco has been doing an exceptional job at this one. And so aside from this, you could also use this for forensic image recognition. And so essentially, the way that it would work is like, let's say that like you have this criminal that is moving across different countries. And essentially, like if you wanted to use like image recognition software, since they're fleeing across different countries, you can't, according to GDPR, like send their image directly to them. So essentially, like homomorphic encryption schemes or fully homomorphic encryption schemes are actually very helpful in forensic image recognition. And so these are the applications to FHE. But essentially, like, even though it's a brilliant technology, it has its limitations. And the limitations is that it is essentially very computationally expensive, and it's very hard to support multiple users at the same time. So FHE does enable computations on encrypted data. But in scenarios involving multiple users, the complexities actually multiply. And typically, each user's data would be encrypted under a unique public key. Managing such disparate data sets, especially with FHE's computational demands, becomes impractical in large-scale situations. And to address this, there have been like a lot of research done in schemes where there are multi-key FHE frameworks that allow simultaneous operations on data sets encrypted with different keys. And this approach actually like introduces like a new sophisticated coordination in key management and system architecture to ensure privacy and efficiency. The second problem is that there's a large computational overhead when you're doing these kind of operations. And essentially, like the computational overhead is one of the, like, I guess, problems that hold back at like further advancements from this field beyond a certain degree. And so essentially, we require a lot of, like, I guess, investment into hardware acceleration frameworks for FHE as well. But so essentially, like the computational overhead is substantially high compared to traditional unencrypted computations. And finally, like there's a limited set of operations that you can do using FHE, and that is a constraint specifically if you want to use nonlinear activation functions while building a neural network, then that becomes a bit of a problem. But so I mean, these are some of the limitations that are involved in using FHE for AI. And so essentially, like the applications of basic, fully homomorphic encryption-based, privacy-enhanced neural networks are actually limited by the computationally expensive evaluations required for deep neural networks on encrypted data. And so, I mean, there's two parts of the privacy problem that actually exist in the context of DNNs. So the first half is for AI solution providers. So, I mean, usually, like, if you're an AI model provider, then you would want to keep, like, the weights of your models private. And essentially, like, there is a mechanism through which what you could do is you could publish only the open networks in your neural network while retaining the private networks on cloud servers. And then the other data privacy issue is for users. So users actually want to keep the input data private, and they still want to get the prediction results. And this is actually something that gets addressed using homomorphic encryption. And so essentially what we've been researching is hybrid FHE-based privacy-enhanced neural network models. And our goal has been to like actually address the inefficiencies of evaluating DNNs on encrypted data by partitioning the network into an open part on the user side and a private part on the cloud server. So essentially, like past research, what it has looked at in the intersection of FHE and AI has been essentially like, how do you split it up, the network, such that there is an open network and a private network? The open network is what actually runs on the edge device, and then the private network is the one that runs in the cloud. And the goal here is that the open network actually runs locally and performs computations in plain text. And then intermediate results are then encrypted using a homomorphic encryption scheme and then sent to a cloud server. Then the cloud server is what actually performs computations on the encrypted data using the private network and returns the encrypted prediction to the user. So only the user possessing the secret key can decrypt and access the final result. And this approach actually effectively reduces inference latency by transferring some computationally intensive ciphertext operations from the server side to the client side. And here on the client side, where, since you're staying on the client side, essentially you can actually use plain text operations instead of having to use ciphertext operations. And so the way that you would be building like an open network here is what you would do is you would like compose it of general feature extraction layers, such as convolutional layers. And then these are actually typically sourced from well-known open source neural networks like FaceNet, TextCNN, and Inception v3. And then for the private network, you can include task-specific lower layers tailored to the data set and application requirements. And so essentially this way what you can do is, like trained by the AI model provider, you can still have proprietary training methods and keep the parameters of the model confidential while simultaneously like making the operations that you run on the local device less computationally expensive. So this is a hybrid FHE-based PENN model. And so this division actually allows for the protection of critical private network parameters within the cloud's like infrastructure, while only the open network layers are actually exposed to the user. And if the entire network were private, the model would align with the traditional FHE PENN framework, making the hybrid model a generalized extension of the basic scheme. And so essentially, what we've been looking at a lot is like, how do you use transfer learning in hybrid FHE-based PENN schemes? And so, I mean, the goal here is like, we want to build a network to solve task B by using dataset D2, by leveraging a pre-trained network on a related task A, which was trained on some dataset D1. And this is the goal. So the first method actually involves freezing all parameters of the pre-trained network. The idea is to use this pre-trained network as a feature extractor. We then add a simple, shallow, fully connected network, typically consisting of 1 or 2 fully connected layers, and train this shallow network on the features extracted from the pre-trained network. And the pre-trained network initially trained on dataset D1, which includes these layers, convolution 1 to n, followed by fully connected layers 1 and 2. and an output layer. And then what we do is, when applying this network to dataset D2, we freeze all the parameters of the convolutional and initial fully connected layers, allowing the pre-trained network to serve as a feature extractor to the new dataset. And then what we're doing is, essentially, we're just adding a shallow classifier. And so essentially, this is a hybrid model setup. And in this way, what happens is the pre-trained network actually remains unmodified and is designated as the open network, operating on the user side and performing computations in plain text. Now, the shallow, fully connected network trained on dataset D2 is considered the private network and operates on the server side, where input and output are managed as ciphertext for privacy. So the open network running locally on the user's device is the one that actually executes the initial feature extraction in plain text. And then the intermediate results are then encrypted using homomorphic encryption and transmitted to the cloud server. And then essentially what we're doing is, like, we're trying to reduce the inference latency by offloading all of the computationally expensive ciphertext operations onto the edge device. And then here on the edge device, the plain text operations are actually less resource intensive. And so essentially the second method, so first method we looked at was freezing some of the parameters. And then the second one is fine-tuning some of the parameters. So essentially in this case, what we're doing is we're still freezing convolutional layers 1 to 3 instead of 1 to n. And then, so we have some layers that are actually frozen in parameters, and then we have convolution 4 to 5, and then fully connected 1, which we actually fine-tune the parameters. So the core idea is to freeze the parameters of the top layers, and what we want to be actually doing is training the lower layers of the pre-trained network together with the shallow, fully connected network on our own dataset D2. And so essentially, like here, this is another mechanism for us to be able to like fine-tune some of the layers while keeping the network private, and like while ensuring that some of the plain text operations are actually being performed on the edge device instead of on the cloud, where there would have to be ciphertext operations instead. So this is actually a method or a scheme that you can use to build like more privacy-enhanced neural networks. And that's it for my presentation for today. And these are the reference papers that I actually used during this presentation. They're incredible papers. It would be great if you could check them out. And if you enjoyed my talk, then you can find me on Twitter at this place, and you can follow Supersight as well. And so we have some time left for questions.